Today I'll be presenting the VLSI tutorial 1, that is picking any logic path as capacitance of the routed path. Now we have divided this into 7 slides to briefly explain the process. Slide number 1 is the introduction to the wire capacitance analysis. Slide number 2 is the logic path selection. Slide number 3, the selected logic path and the role of the GF180 MCU. Slide number 4 is the parameter overview. Slide number 5 contains the capacitance calculation method and the calculation execution. And then slide number 6 is the result analysis and the implications. And then the last slide, slide number 7, is the conclusions and the takeaways. Now, I would talk myself, Firdaus, Om Prakash, and Abdul Fattah. Okay, now introduction to the wire capacitance analysis. We're using the static timing analysis or STA. This serves as the guardian of the signal integrity and the benchmark for the circuit performance. By focusing on the wire capacitance, we can dissect a pivotal component that influences how a circuit handles electrical charge and communicates signal. This foundation is crucial for the whole process. Now, going to the next slide is the logic path selection. The chosen logic path selection in this case is 1123/I to 1123/Z. Now, the criteria for the selection is based on the STA report inside. The selection of this path was not arbitrary, meaning not random. It was chosen based on the combination of parameters such as the fan out, the capacitance, and the signal slew. All of these, when optimized, can lead to significant improvements in the circuit behavior. And next is the selected logic path and the rule. This is the logic path screenshot from the STA report that we have run in the program. And we have selected this here, number 9, the fan out 9, as you can see, in the capacitance 0.06. And then this is the GF180 MCU. What does that stand for? GF180 MCU indicate the technology or process node that used for design, referring to the 180 nanometer technology node from a specific foundry. In this case, is GF is the global foundries. And then the FD underscore IC that stands for full depleted silicon on insulator, FD-SOI. This with a standard cell SC design methodology. FD-SOI is a technology that provides reduced power consumption and improved performance compared to the traditional bulk silicon processors. And while MCU 75V0 here indicates a specific metal stack configuration or threshold voltage, characteristic for the technology. So MCU stands for metal configuration unit, and the 75V0 here indicate the specific of the configurations. And then the buff underscore 2, this is a buffer basic logic element that used to strengthen the driving capability of a circuit. The 2 indicates the specific type or size of buffer, denoting the number of stages, strength, and or other electrical characteristics. In this context of path in the VLSI design, this buffer is used to ensure that the signal can be transmitted effectively from the start point 1123/I to the endpoint 1123/Z without degradation despite loading effects of the fan out. And then we're coming to the parameter overview. Parameter overview here is that the fan out, the number of gates inputs connected to the output of the logic gate. And then the capacitance or cap, that means the ability of the wire to hold an electrical charges in the nanoscale range. And then the slew rate I to Z, that is the speed at which the signal changes from low to high. And path delay means the time taken from a signal to travel from start point to and endpoint. Okay, we coming to the slide 5, that is the capacitance calculation method for the selected logic path. Here the screenshot of the selected logic path. As you can see here, this is the fan out. So this is the data. And then the calculation execution is actually very simple. Is exactly the based on the formula Y capacitance that equal to the capacitance divided by the square root of fan out. And then we can substitute the value that we have from the screenshot into that we have from the STA report into the formula. So this is the calculation that you can see that the fan out is 9, the capacitance is 0.06, the slew I is 0.27, the slew Z is 0.75, and then the delay is 0.68. With the formula, we got this wire capacitance equal or approximately to 0.02. Therefore, that is the wire capacitance. Now, that's the calculation result. For the result, we can have the analysis of this calculated wire capacitance. Okay, back again, that is 0.02. So this calculated value has several implications to the overall circuit's performance. The signal delay is that when capacitance directly affects the RC delay of a circuit where R is the resistance, C is the capacitance. A higher capacitance can lead to a longer delays that slowing down the circuit. Number two, the second implication is the power consumption. Capacitance impacts the dynamic power consumption as power is consumed every time a capacitor charges or discharges. So a larger capacitance increase the power consumptions. And the third key implication is the crosstalk. The higher capacitance can lead to a crosstalk, which is the interference caused by capacitive coupling between adjacent wires. This can degrade the signal integrity and lead to a logic errors if not properly managed. Now, understanding and managing the wire is essential to optimize this aspect, thus ensuring the circuit meets its desired performance requirements. And we've come to the final slide, that is the conclusion based on this. And as we analyze this wire capacitance, in this case using the GF108 MCU, it has informed us about the timing, behavior, and the signal integrity within a VLSI circuit. By understanding the capacitance along the specific paths, engineers can make an informed decision about buffer placement, wire sizing, and routing to reduce the delay and minimizing power consumption and also improve overall chip performance. The next steps after this analysis will be the following. These are the four that we have summarized. Number one is that to identify the other critical path. This can be done using the STA reports to pinpoint additional critical path that may benefit from similar optimization. Number two is the optimization by applying the insight gained from initial analysis to this new path, adjusting design elements like buffer, drivers, and routing to enhance the performance. Number three is the iterative improvement, which if path optimized, the design is incrementally improved. This iterative process continues until all critical paths meet the desired performance metrics. And number four is the verification and validation. After optimization, the updated design is subjected to a rigorous verification to ensure it meets all functional and timing requirements. So by systematically analyzing and optimizing each critical path, the overall design becomes more robust, more efficient, and capable of meeting the stringent performance criteria. So well done, that's it. That's the end of our tutorial one, and we would like to thank everyone. Thank you.